So what this correlation is giving us is, this is the friction factor for a fully developed flow. Right, fully developed flow in a duct. Hopefully you've seen this before, right? This is fluids. Have you all seen this before? Yeah? For the most part? Okay. So what are we looking at? This is the friction factor for flow in a duct in fully developed region. And you can see maybe some interesting things here. So first of all, it's in terms of Reynolds number. So the Reynolds number down here. So if I can compute the Reynolds number in terms of the length of the pipe or whatever it is, this is, you plug that in and you sort of go into your chart. But there's maybe two different regions that you care about. One is the laminar region over here. And so in the laminar region, we're going to model the friction factor according to these basically log linear. It's like linear in a log scale for these different things. But the thing to point out here is what's important on the left is not the same as what's important on the right. So what's important on the left is things like the duct shape. So we have a circular tube, we have a square duct, we have parallel plates, annular duct, right? These are different geometries. Okay, contrast that with what's going on the right in the turbulent region. In the turbulent region, remember everything's dominated by the viscous sublayer. The viscous sublayer doesn't care what your shape is, right? It's much smaller than your shape. So what it does care about is the things that it's the same scale as, like the relative roughness. So this E over DH, this relative roughness, you have to compute that and then plug it in and use it for these different values. So here, different values of relative roughness are going to give you different friction factors. All right, so this is basically how you'd use it. Let me give, so this circular duct, the friction factor in the fully developed region is 64 over Reynolds in terms of DH. And so that's, let's see this one here. I've also put on here a rectangular duct. Sorry, I didn't put that rectangular. And so the rectangular formula is this. It's a little bit more complicated, but basically it's just to accommodate different area or aspect ratios. The aspect ratio is the length of one side of the duct over the length of the other side of the duct. So you just compute that, plug it in. Let's see, if you want to account for, this is a separate note down here, but if you want to account for the developing region, you can do that with this correction. So you take the fully developed friction factor and then scale it basically according to this formula. All right? So this is like an example of the correlation. Another example of a correlation in terms of the Nusselt number is here. So again, we see the same type of behavior where the laminar region is different from the turbulent. In the laminar, we have geometry is important. Right? Geometry is important. But the interesting thing is actually the Nusselt number doesn't change. Right? Our non-dimensional heat transfer coefficient doesn't depend on the Reynolds number in laminar flow. Right? And I guess that sort of makes sense because your velocity profile is the same. Right? Your velocity profile is the same regardless of the Reynolds number. So some maybe values to keep in mind. You can memorize these. I'm sure you will. So for a circular duct, the Nusselt number, fully developed, is equal to 4.36 if it's constant flux. Nusselt number, FD, is equal to 3.66 if it's constant temperature. All right, so if I tell you it's a circular duct and I tell you that it's laminar, you don't have to know anything else to compute the Nusselt number. You just know it, right? It's kind of interesting. All right, let's see some other things here. Turbulent flow, if you want to go to the turbulent region, then there's, and so the correlation is given down there in the bottom, and that just tells you the family of curves that are on the right. So this is called the Nolinsky correlation. You'd probably want to use this for any turbulent situation. All right, so you can kind of go back to these or look at these if you need to.